creo que ni griego puedo dar esa charla. La terminología en francés o en español es más fácil que la terminología en griego, así que me voy a darla en inglés. Era un ejercicio un poco difícil porque quería hablar de lo IAFER, que se acaba, voy a dar los detalles, que se acaba en 2 años más o menos. Pero yo tengo un perfil no muy típico, digamos, de informática o de IA, pero hay algo en mi trabajo de investigación que es común, más o menos matemática aplicada. Del momento que hay temas con preguntas fundamentales, a mí me interesa, en principio. Entonces, también quería enseñar cosas de lo IAC, cosas que hago en aprendizaje automático, distribuido, que tienen conexión con el IAC también. Y cosas también que cuento hacer un poco más tarde. Les voy a pasar en inglés. So, the outline, as I explained, it was more or less. The first part, I'm going to do it, a bit explain you about the ERC, which is not on machine learning or AI per se. Okay? It is related about the intelligence in the edge, but it has more a focus on data processing, but also transporting, transmission, reconstruction. Okay? So it's not only pure data processing of big data, but I'll show you the connection because this is driven by where we are going. Okay? So I wrote it 2019, I got in 2020, started April 2021, so it's 5 years. So it goes until March 2026. Now, given that that was the COVID period, so I have like 6 months to get the first students and so on, I count on asking an extension to work. I mean, because, you know, there is still some funding to spend on the ERC, so I have more time, okay? And in any case, these are topics that, you know, the ERC you start already, I wrote it in 2019, it means that these are ideas in my mind for a long time, before 2019. So then it get mature, and these are things that also evolve. So for people that they try to write an ERC, you won't have the answers of what you propose, the total thing of the answers, because the things is evolving. You have an idea that is something behind somewhere. You know, and this is why you try to persuade, that you do a radical view on what has been done. And I'll show you, I have some slides which are not on, you know, let's say AI or machine learning. It's more information theory, which is one of my core expertise, which actually gives the motivation behind this. I'll present some of the things I'm doing on, you know, AI, a lot of things on distributed machine learning and federated learning. Lately with Bayesian as well, with some connections with the ERC. I think I won't have time to present the trustworthy and the multi-agent, but these are topics. I put some, you know, keywords for things that I'm interested, and for people that they are working on these kind of things, we can discuss. So that's also the idea of the talk, is to, you know, see things and keywords that you are interested, then we can discuss, so that we can open collaborations and so on. And a bit where I'm going, but this is very, very, very big. So, let's start with the motivation, and let's do a fast forward to 2030. Okay, I told you I wrote in 2019. Let's think about 2030, and this is always what we have to do. So, we go to we think that we're going to enter the era of hyperconnectivity, a lot of distributed intelligence, a bunch of sensors which are smart now. They don't only just collect data from the environment, but they can process, they can do training, they can make decisions based on AI. So we're going to have a bunch of cyber-physical systems and interactive systems. So agents basically interacting with the environment, making decisions together with the humans as well in a collaborative manner. Think about all these applications: swarm robotics, smart manufacturing, self-driving cars, and all these things, okay? So we're going to have to do AI on the networks, over the networks. We're going to also have networks for AI as well. So this is the interplay where, you know, some works that I have done in the past on networks and information theory will be 8 counts. But we're going to have all these network intelligence systems that they will need real-time communication, reliable as well, all the time, okay? No doubt about this. But then they will have to do, there will be autonomous systems, have to do a lot of decision making on an automated and autonomous manner, actuate on a timely manner. Certain things have to be very, very accurate. For example, self-driving cars. I'm giving the command to turn left or right. This has to be done in a timely manner. I cannot wait for long. It will have a lot of collaborative interactions. Computation is going to be more tricky. You can have a point as well. Okay, but then the screen doesn't work. And of course, we have to rely on these systems, especially the more autonomous they become, the more we have to be able to explain the decisions, interpret the results, and be trustworthy. Okay? So, one of the examples is like, this is from, you know, downtown Paris. And you have all these, one of the most difficult things to drive here. So imagine all these cars now being self-driving. There's no driver. Just exchange information among the other. They have to do a collaborative maneuver so that they don't crash. The way we will do it now, even with the current networks, will be the typical thing. We broadcast whatever information we have to the others, or to a base station, or to the cloud. Do the processing, do the AI, do the decision, send it back. This doesn't work. It can work for 1, 2, 3, it doesn't scale. Okay? And most of these examples, when we're going to have this cyber physical system, it won't scale. No matter whether we have 5G, 6G, and so on. Because the problem is the paradigm, the way we treat information. And that's the key point. So if you want that they arrive to a consensus in a timely manner, then you need to change the way you basically, you observe the environment, you collect data, you process data, and you exchange information with the others. Okay? And this is the starting point. So basically, we're not talking about in the future Internet of Things, it's more or less Internet of Agents, but the key problem what it's going to be. We're going to have to acquire, process, transport, reconstruct, fuse especially. I'm going to talk a lot about point-to-point things, but the difficult problem is the multi-source, multi-point, multi-point. But we're going there. I have a massive amount of data, okay? And on the top of that, I will have to do my work, wherever is your angle of attack, with a lot of constraints in terms of resources, energy, even if it's communication, if it's processing. Now, for the moment, you know, communication networks have passed this thing of it's okay, we have bandwidth to do things. Now AI is going to that. We'll have GPUs, let's train the big models. Soon, we're going to have to change the paradigm on that as well. Because this doesn't scale as well. You know, train GPTs and put more and more GPUs in these big data centers. For energy, for even exchange of information, computational resources, and so on. And on the top of that, if you want explainability, trustworthiness, fairness, and so on, this doesn't scale easily. Okay, it's a very difficult problem. Okay? But what is interesting in terms of the fundamentals, you have to treat data, which comes from different cues. You have multimodality. You have them representing high-dimensional. They have high-dimensional distribution and anon as well. And as well, you have the geo-distribution. So to get knowledge, to get intelligence, you need to fetch data probably from different areas. Okay? So the big question is that, do we have a theory and then the algorithms to that to be able to deal with this difficult problem? And this will allow us to have intelligence, and ideally general intelligence, artificial intelligence, close to where information is and data are created in the edge. Okay? So, small, let's say, excuse me for this information theory, I know it's not your favorite thing, but we have to go there, and this is as fundamental as it goes. So, what we have done so far, I don't have many slides on this, but we have this guy here, Shannon, with his similar work, which is basically when they quantify information. I don't want to go to the details, but basically the way we design systems, and actually even other pipelines, not only communication system networks and so on, comes from that model. Nobody has challenging him from the 50s, basically, until now. Okay? So we don't care about what we transmit. We don't care about the signal. It's a reliability problem. Everything is the noise here in the middle. And he did a master stroke, as we call. He took the semantics out of the picture. Semantics meaning, what do I carry? What kind of data I process and I send on the other end? Okay? What is the meaning of this data? And what is the effect that will have? Why he did it? Because the problem is very difficult. And this is more or less what we're trying to solve with the ERC. But the more we study the problem, the more we understand why he was brilliant of doing that. Because it was impossible to solve the problem. And there's another thing as well, which people forget, even people doing telecom and so on, is that the encoder and decoder are centrally designed or jointly designed. So you have a multi-agent system. You have two different cards coming from different manufacturers. Even simpler, you have two devices with different software updates. They don't speak the same language. They're not even jointly designed. First, in order to be able to exchange data, they will have to have a common language, common protocol before that. This is taken for granted in our networks today, but not in multi-agent systems when we want to have, for example, LLM agents talk the one to the other, and they might not come even from the same thing. They're not. And we don't hope to be able to centralize everything. Doesn't scale. Okay, so.
No? Okay. But Betty will work in federated learning, and you also is now really you have a federated learning. In fact, we have a platform. We have a platform, flexible, is open in GitHub. Okay? Is in GitHub our platform. Both of them was collaborating in the platform. Is also Junis also working in federated learning. He has integrated client selection, a potential quality of the client, and so on. Really, the things in federated learning, also Vicky is connected with me, the team, but Vicky is now organizes on aspect of the project, really, and Nuria is the postdoc. In the federated learning, we have an important thing. We have several publications. We have been working in attacks. You have been working in blockchain and the quality of the data. Different papers about attack. June is working in client. Betty is working in the aggregation of transformers and the future extension to LLMs and anomaly detection. Really, and Nuria, the PhD the thesis was about attack, different kind of attacks. And then really, in the area of federated learning will be very easy, the collaboration with your team.
So yeah, because basically the things that have to do with information theory, they go, they have faith.
Yes.
Okay? I keep the information theory and all the entropic tools for, AI and machine learning. The fundamentals of statistics and information theory, what drives me in machine learning. But then in federated learning, we have done, I'm just saying in summary as well, because you will be gone by that time. But that thing's a lot more personalized, because, as I said, my model is not your model. Maybe there's a global model that works for everybody, but I'm a specialist on something, so I have very, very specific intent to do. What's the point collaborate if the others has nothing to do with my data and so on? So personalization is something, but also there's interesting things there. In the Transformations as well, we have done things on intrusion detection, mostly trying to use distances and divergences for the confidence interval as well. And now we are seeing the conformal learning, what is gonna give us there. Also have a student that is checking the shield.
Yes,
the one we do with the KL.
Yeah, the seal is the seal is the explainable. Is Ivan is here? Ivan is the.
So
he's the author. Ivan is the leader of seal.
Because the background I have from information theory is basic divergences. So I think we can do better stuff by doing divergences and so on. So we can discuss on this. Yeah. The KL is nice, but the idea is nice.
We have now an extension of seal. The second. You have in archive the first version. Now we have the second version, an advanced version that will be submitted in 2 days, more or less, to you now. And Ivan, honestly, Ivan is working. Ivan is working in an extension of the paper in order to submit, and Ivan will have the paper in 2 days, more or less. No, in 2 days, more or less, I will receive a new version to check, but we will send you a new version. But of course, with Ivan, you can discuss about that.
So if you want, for me, if we look a bit at the future, what's going to be the tricky part of trustworthiness is all these foundation agents or the AI agents. So suppose that many things will be automated. So I have my small LLM, so that my agents go book tickets for me, for example, or do write emails for me. Okay. Now what's going to happen is that these agents are trained. Probably they collaborate with other agents that they are trained in a different way. So even if my agent is fair, ethical, whatever it is, we will collaborate with others that they don't have the same guarantees as for me. Not to say, how do I say that my agent is trustworthy or ethical? I need to find a way, right? And probably one way that we're trying to do now is to have models of trust, the same way we do with our friends, right? Yes. I put the proxy. I make a data set, I make inputs, and then I have an output that I expect to have, because this is my ethical or my, let's say, my level of fairness that I want to guarantee. Train on that, then I have to see how much it deviates, then it comes to divergences in this kind of model, from the expected behavior. Now, when these systems are going to be put in a multi-agent environment, and collect information or fuse information from agents that I cannot control, that is going to be tricky. Because even if locally my agent or whatever I can control, it can be trustworthy. Put this animal onto the jungle of heterogeneity that it has, how do I guarantee? So I need metrics, I need formal ways of measuring how much I deviate, not necessarily going to why we do this decision. So these are topics that for me is difficult, and that's why I use the background from information theory, because it goes to metrics, either divergence or information geometry. It goes back to that. Fairness, for example, I have worked on fairness, and I still work with the student. The problem with fairness is, as we have with trustworthiness, is which metric. In fairness, we have 30 definitions. We talk about with sociology because they have nice things, but then most of them have a hard time to translate in maths to solve the problem. So I can give the big vision, but then to solve the problem, I need to have a model and a metric. In trustworthiness as well, it's a big umbrella, but then we need to find the metrics. There are very, very few work, and Granada is one of the top of where you see like things done in a mathematical way. So I did the jump towards the end, but it's also interesting to you because from all the stuff, whatever has to do with a mathematical framework or tools from information theory, divergence, information geometry, optimal transport that would work a lot. These are our arsenal to attack a problem and put the mathematics into these ideas that we want to have. This is the problems I like to solve. So anything that goes into the AI ML that has to do, a multi-agent problem, dynamical as well, reinforcement learning, because comes the background MDB. So whatever has math, applied math, it's fine for me. So we can work. And
sorry, you can continue. You have now the slide. Sorry, I must go to the TV. Sorry, a lot of Marius.
Yeah, so that's why we discussed the last part.
We have next week and the next time we have a lot of. It's very important. Tomorrow via email we discuss about to prepare the application of the new contracts because now we have the candidates and then you can prepare. I suppose Alberto is now in the classes. He told me that he went to the class, but he will send you the curriculum vitae and then we can discuss. Okay? Okay. Please continue. Disculpa.
La pregunta está bien, podéis hacerlo en español, no hay problema. Mi respuesta va a estar mejor si lo digo en inglés, por los temas de investigación, pero después lo debo mezclar. A ver si funciona. Sí. Entonces, ¿qué? So what did we do? The starting point is to say this doesn't scale anymore, because the way with your agents or your, when you do ML over the network, the way you exchange information in whatever system you take, wireless or whatever it is, basically engineers take this approach. Is that traffic or data comes exogenous. Somebody else gave me data. I found myself with the data set. I don't control how it's collected. I don't know the quality. I don't know why I have to transfer. People in the physical layer, math layer, which is like basically when they transmit or transport data over the network, this is a pipe which is completely, close to them. Just send the data, reconstruct on the other side. Somebody will use them. Somebody will want them. Okay, that's the only way. I just simplify this thing. So this doesn't scale, and this is where it comes this semantics-empowered approaches to collaborating. Is that why in the first place I need to collect and process data? There is a goal at the end, right? There is a user that, or an application. When I say user, client, it's an application that has certain requirements. I don't know, I want to have a robot that hits the left and right with a hammer. I have somebody who remotely manipulates a car, whatever it is. Think of whatever application, remote surgery. There is certain requirements, and if I want to have a scalable system that can operate under all these constraints, then I need to start from the data collection. I need to ask myself, why do I I see a source, I see a phenomenon, a physical phenomenon. Why I do collect data and how should I collect the data so that it's more meaningful and more important for the application I'm serving? Typical example, I have a surveillance camera, okay, at night here. Okay, the typical approach is, okay, I take the picture, I compress it, do whatever you want, send it on a remote end, and the remote end says, oh, nobody has sent it, so I can do that periodically, smart whatever it is. Now, if I tell you, I don't care about whatever you send me, I care to find whether a person with a red hat crossed that line. What is the best approach? All the pictures that have sent so that the cloud or a processor or somebody else at the end will do an algorithm, a process, a construct, and say, okay, do I have somebody hat? No. These are bits, these are information, energy, processing wasted because I don't care about the information. Okay? What do I care to find things? So then I put the intelligence already when I collect. So the notion of something is like I acquire certain data, I sample my source, which is a stochastic process basically, let's say, or a phenomenon, when I have to do it, so that when I send this information, that's the only thing I care. And with that information, let's say, with the least amount of information, the other person will make a decision, could act, etc., etc. That's the whole concept. Okay. Now, how to do that? There is a bunch of things that we have to change, and the problem is it's a joint problem. We can even show that theoretically of data acquisition, data generation. Actually, not even acquisition. It's like I generate at will. I see a source, and I have to have algorithms and intelligence to get the data when I have to do it, given why I send them and for which region I send them. Okay, jointly with whether we will arrive or not, to have the right channel, and how do we reconstruct them so that the application is served the best. Why I say the transmission as well is important, because suppose that what you hear is something fresh information. You have to make decision based on the actual value of one end. Okay, I take the latest information. But if when I send it, it doesn't go through because I have congestion or because I have other problems, there's no point keep sending the same information. Because if my source has evolved, if my information, I have new data on that, new value, there's no point sending the old value. I send a new one. Or there's not even point go and sample, go and take that value, given that my channel is not good. And why do I care? For example, we have robots doing exploration. They have battery limitation, they have energy. So sometimes you want to save energy if you know that there's no point getting that information, or you have a limited budget on this. All these problems enter into that thing. And basically that's why the ERC back then got a bit in the spotlight, because basically it changed the way we do all that things for these applications. Now has become a big buzzword, it's in a different community. But back then, basically nobody was talking because the problem theoretically is very hard. Now, the big question, which is goal-oriented. ¿Hasta qué hora puedo hablar? Porque ahora hemos calculado, hemos tenido eso, no sé qué.
Ha empezado a las 12. Entonces, más o menos lo que tú tuvieras preparado. 50 minutos o tu hora.
Porque como he hecho
un corte
también, un corte intermedio, un corte, hemos hablado, voy adaptando. So, I'm gonna pass all that stuff. So, one thing, this is important because now you can most with CS background, so there's semantic web, okay? So, semantic segmentation, all that stuff. So basically, we know what semantic is. Now, there's a big confusion here, in the sense of like, first we needed to define what is semantics of information or semantics of data. And this comes a bit of confusion because the definition we gave, I gave and some other people, at least the use that we're doing, it comes from Greek, which is significant, and it's nothing to do with the meaning. It's not the meaning. It's how important, how valuable is the information or the data that I have to send. Some people call it pragmatic, whatever, because in linguistics and things like this, these are debates. As long as we define, that's fine. Now, the biggest problem is that how to define what is the important information. Why we have definition on the quality information, we have definitions on the value information, we need to find what is the semantic information. One thing is to define it, the second thing is having tools or metrics to measure it. Okay. Now, in the definition, that was the first definition. I will go very, very fast. I will basically do a bit of filtering of things that I think you are more interested to go directly to the connection with the AI. So at the first level, semantic is you have a distribution, right? You want to make your samples from a data set. Okay. Now, in machine learning, we are used to, okay, the more the merrier, right? Give me more data. Now, if I have limitations, or if I have to do some kind of course selection, I have to train for a limited amount of time, then in the data set, for specific applications, of course, there should be some samples that are more important than the others. So if I train based on that, I already arrive to a certain accuracy, maybe not the best one, but I have no more time. But if somebody tells me, you're in a car, that will give you an image, you have to do some processing, which are the samples you need to get so that at least you have a certain confidence to do that, then you have to go and build your data set in a way so that it's important. So then you have to do a data evaluation from that. So this is the first of what we call microscopic level. It could be on an information source, for people working on, fake news and so on, and etc., etc. It can be also in stochastic process. You don't care. Each one picks its favorite application. The second thing is these agents, when they're going to have the data, they will exchange information over the network or links, so they will start to interact and exchange information. This is the second level that we'll have to define which information should circulate, basically, should be exchanged in the agents, so that I can make my business better. As simple as that. The third one, the microscopic, is a very end-to-end, forget it. That was, forget in the sense of that was the most fundamental problem that is extremely, I think, out of anything I have done. But if you want, I can give you a small parenthesis. Basically, at the end of the day, the fundamental problem is this. I have an event, or I have information generated at a certain point in time and space, right? And at the end of the day, this is an event that represents the reality or the way I see the world. And basically, I reproduce it, whatever process I do, transmission, and so on. I don't care. I have to reproduce it at another point in space and time, right? So this is the fundamental problem of basically data transfer from knowledge transfer. The way to define it comes from basically spatiotemporal geometry inspired by relativity. So we'll do things on that. So for people that like physics as well, we may have a paper on, we're starting doing some geometry basically for this kind of problem, with some reference frames and so on, about the importance, because the context comes into play. And the context is a way of, something is important for certain application, for the context, and it's basically relative relational, right? Changing the context, which is a reference frame, the same as the mobility in relativity, I perceive information in a different way. The importance of information in a different way. Exactly, this is the inspiration, the analogy. It turns out that we solved the Nobel conjectures on when information or processing is more efficient, whether we're on Earth or in a relativistic, based on the spacecraft. There was an open conjecture with some harmonic analysis diversity. We solved that. So sometimes we're having fun on this as well. So I'll skip this part in the sense of like the first way to try and say what is the quality of data, the value of data, and so on is with some new, basically, we build on the entropic metrics and we generalize them. Okay. But what is important is that information is valuable and important to the user based on the context of use. Something is very, very important for me if I do some critical decision making or not. For example, the temperature, I take a measurement of the temperature. If I care only about the room, 1 decimal is fine, right? We don't really care, not even. But if I do something, the temperature on a nuclear plant, probably I will need an accuracy and resolution and precision which is very, very high. So one measurement could be valuable or not depending on the application as well. So what happened here, and that there was a game changer in the way of doing data. We have a tendency to have push system, which is like data is here and I push them to somebody, right? It's the vice versa thing. It's the observer, it's the final user that says whether it was important or not. Maybe I did all this processing for nothing. So everything, the valuation comes from the observer, decision maker, whatever it is, the user of information. And this is what changed the whole thing. This is similar to, for people from CS, the queries are doing databases. It's a query basically that I ask information, I describe what is my intent, what I want to do. Then the network and all the machine learning and all the algorithms should be adapted to that so that they give me the best result. That's exactly it. But this, seeing the things on the opposite side changes a lot of things. Okay? Now, at the end, because this will end up having autonomous system, having multiple agents interacting the one with the other. Now with these LLMs and so on, we'll have foundation agents. We want not only just be users of information, single ones, just broadcasting information and so on. What you want is basically to reason and understand. That's a very, very difficult problem. It's something that we're trying to use some tools to bring the reasoning into the foundation models, and of course, all these ethical aspects that we want, okay? Another thing as well, and I put that because I know there are people that in the past have worked on information fusion and fuzzy systems, so this can ring a bell. One of the tools that we need to work on, which has application on the semantic of information and data evaluation, but it goes beyond that actually, and I think in the future with the agents we'll see them, is basically this multivariate information theory, where basically I have a target variable and I want to find, I collect information from different sources, I want to find which part is redundant, which part is synergetic, and which part is basically unique. Typical thing, you have a box, you have 3 cameras, left, right, and middle. You get the one camera, the right part, and the left part, you put them together, you get the box. You have something in the middle that gets a fraction of the two. So, depending on which camera works or doesn't work, you see things that are redundant, or things that are unique, or things that together, they have a synergetic thing. So that was in the past, for those who are familiar, all these ideas of partial information decomposition, which has evolved into what we call this all information now. So we use these metrics to basically try to find the dependencies that we have in information fusion problems. Now, this, for example, this multivariate information theory of these tools, you go to somebody doing information theory for networks, and they shoot you because basically this doesn't have an operational meaning, it doesn't have a coding and so on. But for capturing dependencies and correlation, these are very meaningful ones. And if you put the dynamics of this, it's very, very deep. So I skip that because this is another metric when we go to the link level, how to get the quality and the value of data. And this has to do with attributes, which is some of them that are inherited and some is contextual. If you want to talk later, I can give you the details. We give a first definition of that. And I go to something. I'm jumping now because I have to adapt a bit. I'm going to something that started from a new framework for the perception, for the way what is important for an observer and what is the perception we have. But it turns out that has a lot of applications on compression, reconstruction, and so on, especially for those who work with variation autoencoders and so on. I don't know, are there any people working with autoencoders? So, the typical thing is normally what we have, if you want to explain, and this is not information theory. The good thing with information theory is it has fundamental things that applies to many things. Even there are people in Stanford explaining that when you do reinforcement learning, basically is that you can show it as a rate distortion problem. Okay. But it's a very general framework that tells you, if you have a source, okay, you have X, whatever this is, an image that belongs to a certain distribution, You want to compress, you have an encoder, you want to compress, whether this is your compressor that we know to do now, it's a neural network, doesn't matter, we'll see later, okay? And then you want to have the minimum amount of bits, the best compression, based on the answer with DaSCI. So this is the rate R, the minimum rate that you can send, so that when I decode and I decompress, I construct the image, I get a certain distortion, right? I get X hat, and then I have a distortion metric here, delta, between basically the original, the input and the output, okay? Typical rate distortion, we know the fundamental limits, blah, blah, blah. This is the optimization problem to solve. What is the minimum mutual information between X and X hat? So how representative is X hat for X, given a certain distortion, okay? Channel rate distortion, but this ignores why I reconstruct the image, okay? Now, let's take this one now. And human perception is very different. And if I send information, we have the tendency to, even people working on images, right, to have a perfect image reconstruction because we think that like this I can make a decision. But what if the other person doesn't care about that, care about specific things? I can even, point the person and put the background, like in Zoom, right? Put the background blurry, because what I care is the speaker, right? So, if the objective is show a picture of a cat with a hat, like this, okay? This is a pixelized one. So, in terms of fidelity, the distortion is bad, okay? Sorry, it has, you do the decompression, get the distortion, okay. You still see that it's a blurry image of that, but you don't see. Visually, it's not pleasing, this color, this photo, right? Now, somebody gives you that. The distortion between these two is very high, right? Nothing to do. But if your goal was to show a cat, a picture of a cat with a hat, that was the semantic. What is important for you to get is this one. Then, for a person, this could be fine. But the distortion doesn't give you that. Typical thing for the people working with the deep fakes, right, with the GANs. Gives you a picture of, oh, this is a person, it doesn't exist, but this is a person, right? It looks fine. And this comes that basically the perceptual quality, what is important for sometimes when we put humans in the loop, you need some kind of metric between the divergence, basically between the distributions of your input and the output, okay? And this gives a different framework, because basically the distortion tells you how different they are. So these two images has a very, very big distortion. The distance basically here is high. But in terms of the distributions, they are closer. Okay? Typical example is this one. So you want to know, this is a bicycle probably, okay? Which one you will use, the upper part of the pictures or the down part of the pictures to do some detection? The upper, right? Well, it turns out that the upper part, which is the good perceptual quality, is the high distortion pictures. This has low SNR pictures, low signature noise ratio pictures. These are the low distortion pictures, but very, very bad perceptual quality. Okay? Why? Because the perceptual quality, something also what we call the realism, what is visually pleasing to the users, does not translate to distortion. Translate to a different constraint that we have to put here, jump here. And it's an extra constraint I have to put on how far are the distributions. So I have X on my pictures coming from the distribution Px. I have the X hat, which is the samples that I should not have them very, very distorted in the mean square error, for example, case. But then if I take the Px hat, the distribution of my reconstructed sample, it should not be that far from the Px. The way to measure this is divergence. So you put in the rate distortion an extra divergence, a distribution constraint. Okay? Could be whatever you want, more or less. I mean, there are certain properties. If divergences work, if Wasserstein works, you can put generalized entropies. You can put the distortion, you can even put, the feature-based from 2016, the Johnson paper. You don't need to go for the mean square error. The problem is that when you put that constraint, the problem is not trivial to solve. The good thing with rate distortion theory, which is a sub-case of information bottleneck for the people that they familiar with that, is that we turn the problem into a convex one. So it works nicely. Here, you don't have convexity all the time, and there's a lot of computational method, especially for general distributions. Not to mention that in most cases, to be able to write things, you have to do certain assumptions that the output distribution is probably the same as the input distribution, and so on. For example, if I have a Gaussian source, then I have jointly Gaussian on the other side. For the optimal case and so on, it's a very tricky mathematical problem. We have done a lot of work on that. For example, if you want to give an idea, this is the rate distortion curves, so number of bits, how much you compress versus mean square error, for different distribution constraints. So you see that the black one here is when I neglect the distribution constraint, and then I have a trade-off. I cannot get low distortion if I have a distribution constraint, depending on how you are. Now, you apply this, for example, to the list, okay? So you see that for low rate, if I compress more, the digits here in the rate distortion without the distribution constraint gets blurry, where here I'm better, right? Depending on how I'm. Now, the trick here is that you check is that what I get here as visually pleasing has nothing to do with my digital physics. Doesn't say that it's accurate representation of the picture. But which one you select the low rate, I think everybody will go for that, right? This is a blurry one, okay? And you can, instead of mean square error, you can put, for example, the feature-based reproduction loss. You improve things even for the sum thing. There's a lot of tricks to reconsider in the lossy compression regime. I'll skip that, but okay. We did a lot of work on the computational methods, on the maths of this. Some cases are easier. For example, if you put alpha divergences in Gaussian, it turns out that you can write things down, actually. Actually, we solve an upper bound of the problem optimization. But it turns out that at the end of the day, just finding roots of a polynomial over the alpha. It's not always fancy, the solution, okay? Just to give you an idea. Now, trying to see what is the implication of that. This is your autoencoder, right? This is your neural network. You have the latent space in the middle, so you have these digits. So the first thing you can do with this framework is to design what we call universal representation. You can fix the encoder, you can vary the decoder in a stochastic way, then you're able to get most of the perception distortion trade-off points you want. This is very simple because you fix the encoder and you don't do joint optimization encoder-decoder, which is also one of the problems you have here if you do autoencoders. What is also very interesting is the connection of these kind of problems, and also everything has to do with bottleneck and autoencoders and so on. If you say that what I have here is an input distribution, but I get a noisy version of that. I get a blurred picture of that. For example, remote sensing, or when you do image restoration. So you have a constraint at the output, but it's not to get something close to that, but to get a clean version of that. So do joint restoration or retrieval and reconstruction at the same time. And of course, you don't want to make this explode. Okay, so basically you put a constraint on the entropy basically of your latent space, because actually you can show that this problem, how to get a clean version which is close to the PX, and also you are into the best basic rate of rate distortion perception, you can turn it as an optimal transfer problem, okay? And actually what we call an entropy regularizing optimal transfer problem. Actually, there is an intriguing connection between rate distortion perception, and optimal transfer. And we can do that. This kind of works is typical. There's a community as well that they have a workshop, compression workshop, Neurips and so on. So this is where also we present these kind of things recently. So the ML community of Neurips are interested in a lot of that. Who works on optimal transfer or has interest in optimal transfer? Theory. Not Okay. So then I skip that, which is that basically in terms of optimization, there is a common underlying structure of these problems. So we managed to bring a new approach with the mutual information, because most people say, oh, you take information theory from, let's say, Shannon and telecommunication. In telecommunication, we have normally random variables. We know the distribution entirely, and this is how the way it goes, right? We can calculate this information. Here we have problems because we have real data that we're not able to calculate even the mutual information. You can put neural estimators, but even that wouldn't work. So we needed a new approach, actually, especially for multivariate problems, and we brought Coppola into play. We saw that this is basically an information geometry projection problem from an optimization point of view. And then we managed to get nice computational methods from an optimization point of view to solve even, constraint rate distortion or rate distortion perception on entropy transfer. Okay. I skip that and that. Okay, and with that slide, I'll go fast in the second part, but I'll tell you, okay, you talk about semantics, which has a lot of networks and so on. What do I care if I come from ML or AI, right? Apart from the fact that I saw that some of you, I see that you are interested. You can use ideas from the semantics information and data to do data evaluation, the quality of your data, what is important, especially if you go away of the paradigm that, GPUs and training is for free. If I start putting constraint on that, especially on multi-agent or real-time content, then you need to do things in a different way, and the semantic will do that. Especially, for example, when the data set has some value in terms of freshness. I want data sets that don't want the statistical information, I want real-time. A big problem as well we'll have now in networks, when we have content which is fabricated by LLMs, basically on these foundation models. But sometimes I want the real content. I don't want the generated image. I want the real image of the person at that moment. How do I able to evaluate these things? And also the things of compression. Now, part of the things that they present comes on basically these are the information theory or the theoretical background, how agents will make decisions, do learning and so on in big networks. Okay, okay, there's big things about cumulative prospect theory. Is anybody working on cumulative prospect theory? No. Okay. And then of course it can help to do basically AI over networks. Okay, but networks not just modulation. I don't care about this kind of things. I'm talking about topology and so on. Okay. Now, since I have 5 minutes, I put some slides on what I explained more or less to Paco before. Of course, I'm not here to do information theory. I'm doing things on AI for quite some time. But I explained a bit the approach of the tools and the maths that I'm doing. So I work a lot on collaborative learning. I don't have to introduce federated learning. You know, and you know there's a bunch of heterogeneous things. We work on even in the past on agnostic federated learning and so on. But let's say the link to the semantics here with the ERC is I have different objectives or goals. Okay. So how do I solve that problem? How do I solve a problem where I don't want to be the global model? Okay, is because these people care to, I don't know, see pictures of game consoles and these kind of things, and other people want to do cooking. Okay, so I have to, in a decentralized, I work a lot on decentralized, not distributed, so serverless federated learning. I have the notion of personalized or intent-driven federated learning where I don't know, I'm expert on, I don't know, specific things on dogs, right? So if I enter to do federated learning to build a generalized model that, I don't know, do classification of cats and dogs, I don't care. What I care is, I don't know, to find the rare species of dogs because this is my own model. This is my data set, this is my interest. So if I join the federated learning group, I will make benefits to others for the generalization. But for me, if there's nobody else that has better or similar data set and interest with me, I won't profit. Because this model doesn't tell me anything. So doing local training would have been better. But now I don't even know whether there is other specialists. So it's like maybe I could profit, and also from a global point of view, the others will profit if I join because I have a very, very, very rich data set of dogs. So there's typical, how to say, not trade-off, but contrasting between the local training loss and the global model. Okay? So we work a lot on how to cluster users based on similarities and so on. I don't have slides. And we also do personalized, basically decentralized federated learning. To give the idea very, very fast, apart from having the personal model, because the idea is that, okay, suppose they have model. Maybe in a network, in a decentralized one, I care only about part of your model. I don't care about your whole model. I care only about the part that you have about dogs. I don't care about fish and whatever it is. So, and suppose you do it on a network, which the connectivity here, I'm not working, as you have imagined. I don't like static things. I don't work with the typical connectivity graph that people are like that and I always communicate. These are random variable things, especially if you put all the wireless things. I don't put it accurately, but the models represent what's the reality. So even my neighborhood change. So I have to find with whom I should probably connect, so that because we have similarity, then I will have my personalized model better. So basically you have a neuralizer, you have the similarity, which is basically a distance or the similarity between the model estimation between the clients. So I'm trying to estimate having certain other neighborhood, which one might have similarity with me. So they're trying to do the same thing in their model training. The way to measure it, go very, very, very fast. Basically, Wasserstein distance. So basically, I'm taking the Wasserstein distance of the logits between two users, and this is the function D that I put basically as an extra term, plus a regularizer, plus the typical federated learning objective function, the typical risk minimization, to solve this personalized model. I go fast in the interest of time. So you see how it works, for example. We have the standalone, which is basically local training. It goes here, of course. In terms of test accuracy, you don't expect to gain much. FedApps, which is the red. FedApps Plus, which is basically this improved federated learning personalization, and our approach, which does evidently better. Otherwise, I wouldn't have proposed. Okay, but that's one trick that we did to do personalization. And any problem on federated learning, especially decentralized, so serverless, that has to do with these things of local training, global model, local model, and so on, is of interest. Other things as well, but I work a lot on distributed things. And as you can imagine, if you talk about distributed learning, whatever has to do with networks, random topologies, and things like that, exploiting my past expertise, I can do that. For example, I used to work on stochastic geometries for big networks. So now we're trying to do basically convergence proof when the topology is random. It turns out when you do the typical convergence proof of FedApp or whatever you want to do, even if it's strictly convex, it's a typical machinery of bounding basically depending on the randomness. Now if you have random topology, according to a point processing space and time, the proof is not that easy. So we're trying to do that with random topologies. So you take into account all the variability you have. And one of the things that I'm doing as well is the Bayesian federated learning, which I explained a bit briefly to Parker. So basically, in addition to the learning phase, you have some kind of estimation of the posterior, the prior and the posterior, basically distribution I will get. So when you do the aggregation phase, basically you take the local posteriors, you aggregate them, you try to find the posterior distribution of the global model. So basically, now it's not finding the model here, find the distribution, okay? The way normally aggregation works here is this kind of thing. It's mostly statistical aggregation, so you take the weighted mean, weighted variance, there's different methods. So what we did here, we did the barycentric aggregation. What is the barycenter? For those Who works a lot on information geometry? Divergence. I mean, divergence you have worked, but you don't know it comes from information geometry. So what happens is that basically, forget the maths. You have distributions, P1, P2, P3, okay? You take the weighted sum, there is a distribution, the manifold basically, that is the one to minimize basically this weighted sum. This is kind of a good decision. The same thing, you have a triangle, you take the things, you take the barycenter, think about that distributions. Okay? Hopefully, this is a distribution that represents nicely all the three. Okay? Same way as the barycenter in the triangle. You can do with alpha divergence, Z divergence, so on. Not all of them are very neat. Even imagine that you start with Gaussians, okay? If you take the alpha divergence to do the barycenter, well, you end up having the barycenter which is not Gaussian. So it doesn't mean you start with distributions or the barycenter will have the same distribution. No, actually. And that's the tricky part if you want to do analysis. It turns out that for reverse KL, we'll back later, and what's this time to, we can analytically, based on the covariance of the Gaussians, if we take the assumptions that the posterior distribution is Gaussian, we can analytically find a way to average this. And it turns out, going fast here, that you do better uncertainty quantification and model calibration, basically. We tested in these three famous, well-known dataset. And basically, you end up having lower expected calibration error and negative log likelihood by adding basically more and more Bayesian layers instead of deterministic. Okay? This is the barycentric. You get things on fairness as well, and linking it with the personalization, we're thinking instead of just doing barycenter with everybody, have a certain region with which I will try to do the barycenter. So basically, I have a certain sphere that does this, and this gives kind of personalization. So I don't go anywhere in this case. Okay, that's a few of the things I'm doing in the ML AI thing. Okay, we do things on trustworthy with conformal learning. We don't have results there yet. We do things on trustworthy intrusion detection with confidence interval, things like that. And whatever has to do with maths and so on. So going very fast. So you tell me, okay, your ERC looks like multi-agent system, but there's a lot of information here, a lot of comments, so on. So you do something on ML, so how do you link all the stuff? You do a bit of everything. It's not actually, the linking thing is the tools and the problems that have to do with a lot of heterogeneous dynamics, hard problems. So where you can convert that? As I said, you have collaborative, this agentic AI. You have agents, not only with model training. Back in 2019, we're saying, oh, you have even learning capabilities. Here, we have an LLM completely. Okay, a lot of autonomy. And these agents will have to exchange information, interact under basically communication constraints on the top of that. So, again, how will make it work? How? Especially if the focus is on trustworthiness, reasoning, causality as well. That's why I think something which I'm not having a result, but if everybody is working on this, I'm studying a lot. Because if you want to go to do that, you have to pass by it. I don't think with pure neuro you can do it. We need the symbolic part to mix them. How and which one? To be seen. The last thing that probably Paco had mentioned is the quantum, which is not, again, because of buzzword. Actually, before becoming engineer, I wanted to become quantum physicist. So one question, but then for pragmatic reasons or because it was most prestigious, I went to the best school. But I did courses on quantum during my undergrads, afterwards, and in France I was teaching. And now that I got the ERC, so I have more freedom to do things. I work back again in the quantum, not only quantum ML. We try a few things, but things in the infancy. I mean, we try to show there is potential, but I mean, you cannot be BERT, for example, for NLPs and so on. I have done things in the past, nothing publishable in the top conference. And now recently I'm even doing, for the time evolution of entropies, quantum entropy, and so on. So you could go from physics up to the quantum ML. So there's a background. So people are interested as well. we can sit down together and do stuff. So that's more or less. I compressed it a bit, hopefully not in a very lossy manner. But I try to give a big panorama of the things that I'm interested, and I'm sure if we sit down over a coffee, we'll find common things. Applications, for example, don't have certain things I only want this application. For me, it's the fundamental questions that we have to ask. So I'm less of like, let's sit down to write an excellent code and kind of things. I'm more into, sit down, find the best mathematical formulation we can find, and then we can write that. That's more or less. So, gracias. Si tenéis preguntas. ¿Es en español o podemos? La próxima vez voy a hacer la charla en español, porque así voy menos rápido. Porque en inglés creo que voy mandando muchos mensajes.
Mejor en español o en inglés. Es que no sé si todos los que estamos aquí hablamos español.
Pues inglés.
O hay alguien que...
En inglés. Yo pensaba que en inglés es solo para mí, pero sí.
Yeah, so you talk about, so in the, I think it was compression and like reconstruction, you talked about the difference between minimizing, I think, distortion and minimizing, I would say, like the loss of semantics, like a semantics loss. And from, if I understood correctly, like these two metrics are like opposing in some sense. So if you care more about semantics, you often you can't minimize at the same time distortion and like semantic loss, I would say. In this example about the cat, like if you want to have like the same image, you get it like noisy, but if you want just to encode whether it's a cat with, right?
Yes. What happened is that basically it's a trade-off. Okay. So
Like
depending which distortion method you have. Normally we take square error. It's easy to analyze. But let's stick to the square error. Okay. Now, which perception you get? It's a statistical divergence. Different the KL, different the Wasserstein, different the total variation. They measure the distance between distribution in a different way.
Based on
semantics. No, even based, it's divergent, has different behavior on the way you say two distributions are close enough or not. I have many ways to do it, the perception, this is a statistical divergence, but measuring, for example, the KL divergence between the distribution, or the reverse KL, or, I don't know, the Hellinger, will give you different things. Its divergence will have its own property from information geometry, will work better in some application or not. So this will give you, depending, here's I think it's total variation, I think. It will give you a curve that, I think this one is not the best. Yeah, this is rate over perception. For this perception constraint, so if you want that the distance does not go below 0.2, this is the distortion curve you can get. So if you tell me I want that distortion, then you cannot compress much.
Okay, so compression like for distortion. And you said that you
and perception, depending on how much you want. So if you want to have what we call perfect realism, the best you can see in terms of perception, then you go this very high, then it will be probably highly distorted. Or you will have, if you want low distortion, then you won't compress much. You start sending more and more bits.
So I don't know if I've understood like where's semantics in that, because you talked about measuring distortion, and I suppose like KL divergence, for example, does not take into consideration the semantics, right? It's only the two distribution, like in semantics.
No. I didn't say that the KL, the distortion only does not take. The divergence is start getting the semantics as translated as perceptual, which means if what I care is not exactly a clean version of my image, a non-distorted version of my image, but I want from a certain image, certain part, let's say, very, very clean.
Yes.
Like here.
Okay.
I want that part very, very clean. The rest, maybe I want it blurry. So instead of doing for distortion, I do it with divergence. whatever that person says me, then if my job is to detect that person, if what is important, so what is significant, so what is semantic for me is the detection or seeing that it's a building and it's not what I don't know what is here, then I'm done. So the divergence is a semantic quality metric or perceptual quality metric. So we translate the focus that you have on what you want to detect here as a perceptual quality metric, which is captured by divergence.
When you talk about perception, that's where semantics is. You're saying like, I want to be able to distinguish a certain type of object or to make a certain type of decision. That's like perception.
It's perception and it changes between people. So I can send the same picture and your business is to collect super high resolution pictures of that building. You will tell me, not even that is good. It's very, very fortunate. But if your thing is, oh, building, I'm fine. So I send the same information to two people. For you that you want the super nice pictures, your importance of that thing is low. Give me better. It has no value for me. For you, I'm done. You don't even have to care and go for lower distortion. I'm done. So the semantics comes that depending on what you want to do.
Yeah.
Okay? You have a different valuation on what they give you. So sometimes, for example, when I say the approximate reconstruction, you don't need to reconstruct the whole information flow. You don't need to reconstruct. You need just the first things that is enough to make a decision. If you see somebody deviating, you don't need to see the whole trajectory of the thing to say, okay, alarm. You see what I mean? Now, the typical thing we do is, okay, this is trajectory here, and the distant twin, okay, I have to reproduce the whole trajectory. If that's your business, yes. But if my business is to avoid passing more than this from the pedestrian, as long as I see that, this is what I care, this is the alarm. The rest, I don't care. So we can send it.
And the other question is that you talked about in the autoencoder, for example, like incorporating semantics into the latent space, right? There was a slide like with an hour semantics into the latent space, the bottleneck.
It's not exactly semantics, but it's actually, this is tools also to design autoencoders.
Yeah.
And what you can do is that the whole problem, you can do it as a radius social perception, but you can also map it as a optimal transform problem, where you control actually here the entropy of the space so that you control the compressibility. Because optimal transform is what? Is the best, is the optimal, is the minimum cost of taking one distribution from one point to the other. And this is actually the fundamental problem. What you do with learning is you have a distribution, have some sort of distribution, you learn them, and you want them to construct on the other side. So you transfer the distribution. The optimal way, optimal in the sense of lower cost, is given by the optimal transfer.
But I mean,
okay, so just a second, you tell me. So here, if you don't control this, then you might end up not even compressing. Your latent space will be very, very rich. So that's why you need to do the entropy realization, and there's another technicality for the optimization.
So basically, like a normal autoencoder would try like to compress information to minimize the reconstruction loss, I guess. So what's different if you care about semantics? So it's like you would, instead of reconstructing the image in, like with high fidelity or whatever, you would obtain an image where it's like another 8, but maybe the shape is different or the background is different, but you can clearly say that it's an 8.
Yes.
That would be semantics.
Yes. And this probably, if you model it like this, your latent space will keep a lot of properties probably that normally when you do this dimensionality reductions you keep. The feature space sometimes keeps them, but the latent space sometimes in variation of the because you don't control. Here with this kind of tools, the latent space has better geometry, but it's not proven.
Okay.
For example, one of the problems we have with Transformación AI with intrusion detection is to be the feature space in the competency interval. The feature space was very nice. We tried to do it on variation methods with latent space. We managed to do it with, again, distances, noise and so on, but it was very, very hard. Because then you have to go to the geometry of the things. And these are the interesting stuff. Not very easy.
Thank you.
So.
Yes, like, how do you define this semantics? Like, if we just care about the background versus the foreground, or we care about the the ground, we are looking at the road to see if it's slippery for a driving car, or we don't care about the sky, these kind of things. Because we're seeing something that seems a bit like in different purpose. Like, in one hand, you said that we should forget multitask and be more ad hoc, goal-based, but then you have goal-based. So it means we are going back to basics. I mean, we don't take advantage anymore of multitask learning and transfer learning, and reconstruction law is usually used for some other objectives, but for a proxy task. So do tasks help each other, or here we are isolating?
I wouldn't go far to say this makes questionable transfer learning and all that stuff. Now, the big question is, tell me, how do I know which reconstruction laws or which method to put for my semantic? That's exactly the key difficulty why Shannon put it out of the picture, because entropy, for example, we want to measure importance, okay? For information theory, the way it works here is surprising. Information that's very surprising carries a lot of information. So low probability event carries a probability. So if I tell you it's going to snow in Sahara, low probability, for some of us would be cool. Why not? But if I tell you low probability now, okay, Valencia, no, but the low probability that there's going to be a thunderstorm next to your house, you're going to run. So the importance of this, two equally low probability, which from the entropy point of view is equally important, without definition information, has different effect. The one you run, the other side you say cool. So the problem is that you try to put maths in subjective metrics. And this is the key difficulty. That's why Shannon took it out. Because when you start having subjective metrics, which depends on your goal, then the risk is you end up by case solution of the problem. This you don't want to do it. So on one side you want to have metrics to get what is important, which is as an objective amount of information, a subjective based on your interest, on how you're going to act and so on. But you want it to have it as universal as possible so that it applies, and it's not like every problem you give me, I define a different thing. So that's why we try to use entropies and these divergences as a way of taking a big class of goals. Now, the key problem, and CS people will like that, is you start from the goal. How do you define a goal? You need a formal algebra. People in the past have done this lambda calculus in computer science. I check all that stuff. More or less we need that, but I'm open to these things. I mean, to talk about these things, we had to go in the past on many others. So lambda calculus, for example, will tell you more or less how to do these kind of things. Because otherwise, how do you define goals? Each one will have its own goal. You have to do the categories. You have to define the intent of the goal, which is a very blurry notion, back to certain guidelines, concrete metrics, which then you have to put them in all the system and change the way you do processing, transformation, and transport and reconstruction under these metrics. So these are building blocks, and this is the ERC. The ERC is something, if we change the way it is, and we'll do the building blocks, and at the end of my ERC, should have 5 years more to finish. And not to mention in a real network, how do you know the goal? I mean, I'm talking about a sensor will know what is the goal, and will sample, we make the data set and the data position in that way. To a simple node in a big network knows what to do, or a cluster knows. But this is engineering. So hopefully, if we show gains, then you put the engineering to do that. But, and this part, for example, these are not questions from the university, but it's good to have them in mind. So at the end of the day, this will, in a practical way, you might have to change the whole way of doing, layering and so on, and metadata in the network, so that you don't rip off the gains from that. But studying this, you have find different frameworks that, this applies, for example, for impression, machine learning, and so on, that came from a different point of view. But yes, how to define the goal, how to define context. I'm still trying to find, and I study all the theories that I have done mathematically for the context. How do I quantify? In information, there is easy, background information, side information. So I have a distribution, and somebody reveals something, I can model that. But if I want to go in the big data, do? I need to find the context, which will make this, depending on the context, the divergence or the construction laws change. Not to mention, the biggest problem is time. The interesting application of this is time varying. And here you didn't see that, because if I put time in information theory, it's difficult. It's not, we do stuff with time a lot, but then or you end up with MDP problems of decision processes, and sometimes you get stuck and you go for a ride. But in the entropy, you don't put time. There are communities doing information theory with time, complex networks and so on. There are physicists doing that. I'm checking their work, but yeah, all these things is time bound. Something else in machine learning we don't care much. Static, big data set here and that. For example, I don't know, for things. But if you start saying that now I have to do detection of, I don't know, wildlife fire, for example, that propagates, statistical data doesn't tell you anything, right? Some samples of which are dated from yesterday or today are more valuable to train than historical data, right? For specific application. There's the notion of age, of freshness of data as well, for certain applications. So this penetrates, so from all this semantic which comes attributes like freshness, it penetrates metrics and things on data science as well, how to do data evaluation. Doesn't really respond to your question, but because it's a hard one.
Yeah, for me, it comes to my mind only things like maybe contrastive learning or learning from human feedback, where you will get encoded somehow, separate these images are of this class, these are from this other, but
yes,
as you say, this is time-leap, and you need a lot of data, and so it's not very.
That's one thing.
Efficient, no?
That's one thing, but also the other thing as well, which I didn't show, it changes even the way, as I told you, basically, you don't know the goal. The problem what you have here is, on one end, you have the data, right? You have your source. So if I'm the sensor, I know the distribution, I can build my data and the data set as much as I want. And I say, based on this data, I can tell what is important, right? Oh, I saw something, jump on the things on the stock market. Oh, it's important, let's inform. But this guy has the goal, right? Bob has the goal, which normally I don't know. I might have an estimation of the goal. So what goes behind that is like, first, this guy will ask, give me information about, I have to do a decision making to buy something on the stock market. Give me now, because now I'm going to take a decision. But what if, in terms of the stochastic process you have, that was not the best moment to ask for information, because more valuable information will come in a minute. This guy doesn't know. He can learn by seeing what kind of distribution this guy, Alice, is here. Now, Alice would think what is important according to an estimation of the goal. So basically, he has to learn also the goal. So Bob has to teach Alice. So it goes that way. This is the input, which is a query, and this is the feedback in the output. And this is a Bayesian kind of information theory, which I'm developing now. And if you do the this is agent, so basically it's finite data. The good thing of that is, for those who are familiar with information theory, you have no data processing equality, which is something that you don't touch in information theory. You have the data processing equality that data cannot add more information, and process does not help in information theory because you have both chains. Here you can show why it helps, and information is not always beneficial. But this is for agents that they have finite set of this. But it changed the whole thing of designing things. You see what I mean? So it doesn't bring solutions to everything, but it will change the way we see certain things, even on learning. I mean, I compress, I don't know, work of 5 years, which is reading of plus, I don't know how many years and ideas of those things. So there's a bunch of them. I present something of that. But the implication, the more you study, the more you see the things and the commonalities of certain things. At the end of the day, it will change the way we design things. And now people are thinking of putting in the standards and so on. That's not my thing. I mean, this went very fast, at least for networks. I mean, in the network communication community, this is the hot topic. I'm going in a different direction.
Have you thought of relaxing the assumption that you don't know the goal? I mean, you know the goal, like we were saying, we are Zoom company, we only care about the foreground. But formalizing this mathematically in a loss function is also not easy. I mean, for that, I think you could do all this contrastive learning and all these things, no?
Yeah, I can do
That's
that.
much easier, but
I can
you
do that.
assume you never know.
No, I start by assuming I know. Where I assume that I know, for example, the statistics of when you design, for example, suppose that you have a decision process here, and I have the stochastic crosswind phenomenon, and I'm trying to match, based on the metrics that I have on the goal, what represents the goal and what is important, and try to match these two things. Basically, we can do it. Dynamic, I mean, MVPs, and basically you end up evaluating the ratio of the If I don't know the goal that is that, I haven't done it. We started with the thing, with all the assumptions that are workable to do the analysis. Now, when I have to estimate, I will have to estimate. I have to get the heat. Any other question? In any case, the idea, I mean, I can show the slides, the idea was to, more or less the things I'm interested in, and I like to collaborate a lot. So, okay, now discuss, or whenever you have, you want to learn what is optimal transfer and so on. I spent a lot of years in France on purpose because, French, the engineering school, they like maths. Basically, most engineers are applied mathematicians undercover. So, I mean, in France, optimal transfer is the standard tool that, But, I mean, recently I saw on MIT, they're trying to use this kind of optimal transfer to see how, to explain a bit how LLMs are working and so on. For the moment, I'm reading. There's some interesting formulations on that. Okay.
Muchísimas
Thank you.
gracias.
Yeah.